Our next speaker is from Siemens, and their product is called Describe, and of course, another German name, Matthias Austum. Okay, welcome.
Okay, thank you. Okay, Describe, another product for automatic authorship identification and clustering. I want to give you some insight of the features we are using in Describe, and I want to show you some results we've done with cluster analysis. Oh, down. Okay. First, I want to start with the postal routes of our company or development group. Then I want to say something about the global OCR functionality. Then something about use cases we want to address with our product. Then a rough overview of the software architecture inside Describe. Some words about feature extractors, which we are using. Then the extensive feature analysis we have done. Something about cluster analysis and potential applications we see in the future. Like Dr. Srihari, our development team is, I think, 35 years in the postal domain active. We have done a lot of projects with USPS together. The 96% read rate are correct, I think. That's inward handwritten text. Siemens currently with this OCR reads everything on a mail piece from return address to recipient address, as well indicia type and endorsements. Overall in the world, I think we have about 150 billion mail pieces per year are processed with Siemens OCR software. And that's our route, and we have developed a software architecture which is very efficient to clean up images and to extract handwritten text lines and to read text lines. That are our roots, and we extended these roots by authorship identification technology. Here, some words about global OCR. Due to the different requirements in our postal customers, we have developed our Artread OCR to read Chinese, Arabic, Cyrillic, Greek, Latin in all national variations, and even the newest project, Devanagari, that's in Hindi writing style, we also are able to read. And great parts of this OCR technology is already integrated in our product Describe. We use it currently as a keyword spotter, so you can type some special keywords we want to look up, and then it gives you the results of it. The use cases we want to address, of course, the same. The other products obviously also address which handwriting from a group of documents is similar to a given handwriting sample. How similar are two handwriting samples? How many authors wrote a set of documents, and how can these be organized by author? Now a short overview of the software architecture behind this. The features we are using are similar to those already mentioned. Special textual level features and allograph features. We have been inspired by ideas from the group in Nijmegen, and some of the figures I want to show later on are from the papers of Bulaku and Schumacher. We start with image acquisition. Then we have our standard pre-processing on the left side, where we try to do an image enhancement. We do a normalization of the image in terms of quality and resolution. And then we process this image to the different feature extractors. And these output of these feature extractors go on the one hand into the word and content analysis for this keyword spotter. And then on the other hand, we do it in a template generator. An important aspect of this template generator is that we weight the features in order to get a normalized input for the matcher on the other side. Then the output of the template generator can deliver input for the matcher, which can compare these templates against the stored template list or watch list, or it can be input for a cluster engine, which can also produce results. Important design aspect from our solution was to give a fast and good result as a first hit. Now I want to just shortly go over the process of pre-processing. We start with 200 dpi gray image as a minimum. We can, of course, process images with larger resolutions. Then we do a pre-processing, line and word segmentation, and then we extract some simple basic features like average height of line, average length of line, average blackness of line, etc. These are all input for the template generator. Then I mentioned before, we evaluated the different slant-based features which you can extract from a contour. We evaluated the contour direction comparison, where here's the character is a bit misleading. We look only at the line contour. We don't segment the characters itself. We look at the entire line contour and calculate an angle in a certain distance over the entire inner and outer contour. This produces at the end a probability that a certain angle is in this writing sample. Here on the lower hand you see on the left hand is a more upright writing style, on the right hand a more slanty style, and you see a significant difference. Then this was the best feature. We have used it also in our product finally in two different approaches. That's a hinge feature. Hinge is somehow two angles which are calculated around a central pixel. And again, we calculate these on the inner and outer contour of the line and not on the characters. Buller proposed also a third method, the direction co-occurrence comparison, but this has not worked very well in our environment, and we have not chosen it to integrate it in our final product. The allograph-based feature extractor looks similar to what Dr. Ganz already said. I think, we segment the line in more smaller graph frames or subgraph frames. We apply just a simple segmentation technique at the minimum of the contour to make very small subgraph frames. We do it initially for a great amount of documents, I think about 1,000 documents, to generate a so-called code book where typical elements of this graph frames are stored. We use a code book size of 500, and if we get now a new document, we segment this line contour again and look, you see it here, it's the red hits, whether these elements are occurring in the code book and which probability this has. This leads us, here we have plotted, see the plot of sample A and sample B with the same writer and with a different writer, and we see here it's common marked the same plots of probabilities that a certain grapheme is in the writer. And by comparing these, you see clearly here it's a different writer because we have here less dots in common than on the other with the same writer. What are the key features of our product? Because the features itself are published before. I think we use our advanced image and processing and improvement algorithm base. We have a very efficient software which leads to a small footprint at the end. We consume low runtime. We have the possibility that we enable large database analysis. And we already have an Android port available, so it should work on a portable device. Now I want to start to the important aspect, the feature analysis. For this feature analysis, we have had 3 data sets. One large English data set with 2,500 documents, a large Arabic data set with 5,000 documents, and another Arabic data set with 1,000 documents, including a lot of unknown writers. And here are exactly the features we are using in our product. We have 2 configurations. one with 4 feature vectors and one with 6 feature vectors. For the cluster analysis, that has been shown that the one with the 6 feature vector was the best. So in the following slides, I will only show graphics which are referring to these 6 features. And in detail, you see here 2 grapheme type feature vectors. One is with the brackets inside, is the vector size. It's a simple split technique, the segmentation technique with 500 dimension of the vector. And then we have another grapheme style where we have not applied the segmentation technique. We just taken the dots and separation marks, which are very small. That has proven to be very significant for some type of handwritten documents. And then we have here the hinge feature in three different configurations, 2 different line configurations you see with the same dimension of 1500, and one where we approximate the contour. We've done some skeleton technique and taken not the inner and outer contour, we've taken the skeleton just. And at last a simple writing direction contour where we have taken a reduced resolution, only 12 bins instead of typically 32. And now here are the results of a transformation of the feature vectors with 2 different methods, with the PCR, with the principal component analysis, and the MDS is multidimensional scaling. We see here in the areas where the most variance is, we see something happening, is something irregular, but we don't see really a clustering effect. So that leads us to the assumption that it's not easy to cluster documents according to the writing style, according to the writers. But we see also that they are, in the larger arrays, are dotted around a single plot, and that is the same for PCA and MDS. And then we have done another experiment. We mixed the data sets with English and Arabic and marked the occurrences of these items with red for Arabic and English for black. And we see here clearly in the first 2 dimensions that these groups can be separated very good. Afterwards, we've done an SVM classifier on it, and we got an accuracy rate of 99.6% in separating the writing styles. I think it's not really a language separation, it's more a writing style or writing system separation. You can differentiate Arabic from Latin, but perhaps not English from German. And now I want to say something about clustering. Clustering, of course, should be that on a set of unknown documents, we, after clustering, have a set of clusters, which each cluster contains exactly all writers which have written the same document, written a document. And what measures we can choose to evaluate clustering? I think we decided for recall and purity. Recall means 100% recall means all writers of all documents from the same writer are in one cluster. That's 100% recall. The purity is only documents of the same writer are in one cluster. And in either case, you want to have, of course, 100% recall and 100% purity. But our experiments with our features have shown that this is not possible because I think that the feature of some writers are very similar. So then we have to, the optimum is maybe somewhere here where not 100% purity is, but a high recall. Therefore, we defined a quality measure which combines these 2 measures. We call it final cluster quality score, where we taken a harmonic mean of purity and recall to reflect the effect that an error putting different writers into the same cluster is not as important as putting the same writer in different clusters, because I want to have perhaps all writers of the same author in the same cluster. Now we've done an extensive analysis with multiple cluster methods and different measures. We tried as cluster methods award clustering, single linkage clustering, complete linkage, average linkage, McQuilty, median, centroid. All these graphs show that here it's this Manhattan single and this is a Manhattan ward. That the Manhattan ward or the Manhattan single was the best one. And here is on this axis is purity and on this is recall. You can see here somehow you can achieve 100% recall with a very low purity, and you can achieve here, it's not completely plotted, 100% purity with a low recall. Here's a dendrogram of the clustering with the wards method. You see here clearly it's separated. Perhaps I have to explain. On the lower level are the clusters where all documents are in, and it's a tree form, so that here you can see starting with 2 clusters, going into more clusters, and here you have to somehow find a point where you can take a cut at the tree to define the height where you cluster. With our cluster quality score, we defined a threshold and found here in this box plot that an optimal, according to our cluster score, was here around 620. As you remember, the English data set we have been using for this has 535 clusters inside, or 507, I think. And that's pretty close to this. And here, in this case, we have here 600 clusters around 100% purity with some exceptions. And we have here above 60% recall with the same cluster amount. Here, verification that this technique is working. We've divided our test set into 10 different samples where we have put some sub-images in it. We have a test sample of 2,500 and make 10 different samples out of it and measured them. So here's the cut height and the cluster quality score. The optimum is always at the same around that. This means that the cluster cut height is not only a property of a certain set, it's a property of the entire spectrum of these mailpiece types or document types. So now some words about potential applications. Of course, with our OCR, we can do keyword screening, as mentioned before. We can do machine translation. And with our OCR capability, we can even integrate other OCR software to a voting. White ID as a biometric measurement. We can screening a question document against the known document. We can do a document-to-document comparison, or we can screen documents against the watch list. And clustering, it has been shown that we can differentiate between handwritten and machine-printed text. We can clustering or classifying the writing system in the feature space, and we can do with some restrictions clustering by author. So what we see is an application is that we perhaps can use this clustering and as well our identification technique to eliminate non-relevant documents out of a large document set. We can perhaps differentiate a large document sets into document sets with probably the same writer. And we can separate, of course, documents according to the writing system, so that the QDE can focus on real relevant documents. Here's the contact information for my colleague Mike Carpenter, who is the product manager for this product. We have not been able to test against the test samples you mentioned before, but we would like to, perhaps, if we have the opportunity to do it. Thank you.
we have any questions from the floor?
I had a couple of questions.
Okay.
One of the things that you discussed as a feature that you used or you considered was the direction of writing. Is that stroke direction, or is that right to left versus left to right, like Arabic versus English, or what were you meaning by that?
The direction of the angle.
Oh, it's slant then. You're talking about slant?
I'll get a fast back. Just a second. Do you mean this?
No,
no,
when you had the six features. That
okay.
6 features.
Okay.
Yes. Yes. The next to the last one, simple writing direction.
Yeah, that's this first one. It's one angle which we achieve if we follow the contour. Okay, I'm staying this way.
Okay. Go ahead.
Sorry about that.
Yeah, no problem. That's an angle which is I've shown before. Oh, sorry.
So it has more to do with the angle. It's not the stroke direction of whether you're writing left to right or right to left or cross bars.
It's somehow it's connected. You go from a center. Oh, sorry.
Sorry.
We go from a central pixel along the contour of the
Yes.
inner contour and outer contour, and then calculate in a certain distance an angle. And this results in a probability of angles in the line.
Okay, and that's what you're referring to as writing direction.
Right.
It has nothing to do with
It's not the writing direction of the entire line.
or the overall, whether the pen is moving right to left or left to right.
No, it's always a probability function.
Okay. And the other question I had was going back one slide, you were talking about, or maybe it was, you had the list of, one more back, I think.
Okay.
Well, maybe not. Never mind.
Before?
You had a list of the number of samples you had.
Yeah.
And are those the samples you used in devising? There we go. Devising this program or
Devising.
or testing it? I wasn't sure.
Yeah. That was the features we've used for cluster analysis, and of course for testing our writer identification capabilities.
Okay, then in the Arabic writers, you list artificial documents, and I don't understand what that is.
This is a data set which contains some real documents and some manufactured documents.
Some normal course of business.
Contrived documents.
Okay, what do you mean by contrived? Sorry. Okay, or an exemplar form of some sort. Okay, thank you.
Okay.
Thank you.